Welcome to the Mechatronics Revolution Fundamentals and Core Concepts. In this lesson, we'll talk about diodes, LEDs or light-emitting diodes, and photodiodes. The objectives of this lesson are to describe the current conducting characteristics of devices called semiconductors. Then we'll discuss the operating principles of diodes, light-emitting diodes, and photodiodes. And finally, we'll talk in depth about the need for flyback diodes when we implement switching circuits for electric motors. Semiconductors are a special type of material that are between conductors and insulators. They exhibit a nonlinear relationship between voltage and current. One thing we know about an element like a resistor is that it has a linear voltage-current response. And that voltage-current response is driven by Ohm's law, which is V equals IR. That voltage-current response is shown at the bottom left, where the slope of that blue line, for a resistor, for instance, or any type of conductor or insulator, that slope of that line is the resistance of the material. Now, the plot on the right shows the voltage-current response for a semiconductor. And you can see that it's not a straight line for a semiconductor. So semiconductors exhibit a nonlinear response, and that nonlinear response can be used for a lot of different purposes in mechatronic circuits. Let's look at that voltage-current response for a particular type of semiconductor called a diode. So a diode is probably one of the simplest semiconductor devices, and its purpose is to allow current only to flow in one direction through a circuit. Diodes are used oftentimes in mechatronic devices for a variety of purposes. For instance, light-emitting diodes. There are certain sensors that are built from diodes, for instance, a photodiode, and then certain types of circuit protection devices like a flyback diode. Now, the symbol for a diode is shown at the bottom left, and the ideal voltage-current response for a diode is shown in the center plot in the slide. You can see that for any negative voltage, no current passes through the diode. And then as soon as the voltage becomes barely positive, then the diode doesn't inhibit current flow in any way, so it essentially has zero resistance. When voltage flows, when the voltage drop across a diode is in the negative direction, we call that a reverse bias. And when it's a positive voltage across a diode, we call that a forward bias configuration. An actual diode does not have those ideal voltage-current response, and instead has a different voltage-current response shown on the right-hand slide here, where for a reverse bias configuration up to a certain negative voltage, there's very little current passing through, and we have essentially a very, very high resistance. At some point, the negative voltage becomes so large that current does start to flow, and that's called the breakdown voltage. And the resulting current is called the avalanche voltage. And then at some forward bias, we do see a finite resistance, but it's still very low. This slide shows diodes in both a forward bias configuration and reverse bias configuration within a circuit. In the forward bias configuration, the diode in forward bias has a very low resistance, and as a result, the current that flows through the circuit will be approximately V equals IR, where V is the voltage source and R is the resistor. In reverse bias, there will be very little current that flows through this circuit as long as V is less than the breakdown voltage. Now, as soon as V exceeds the breakdown voltage, there will be current flowing through this circuit. But generally speaking, reverse biasing a diode, when we do that, we usually do that in order to eliminate current flow in a certain direction. There's a certain type of diode called a light-emitting diode that's very well known, and that's called an LED. Light-emitting diodes are a particular type of diode that emit light when they're forward biased. Now, for these diodes, there's a static voltage drop of about 2 to 4 volts when current flows through that LED. So when it's forward biased and current's flowing through it, we see a static voltage drop of about 2 to 4 volts. The color that the LED emits is determined either by the semiconductor material within that diode or the plastic housing over the diode. The circuit symbol for an LED is shown in this slide, and at the bottom left we can see a very simple circuit that will cause an LED to emit light. And you can create this using just an LED, a resistor, and a voltage source. This typical blue LED costs about 50 cents, and it has a 3.4 volt drop when forward biased. It's important to note that you can blow out LEDs by putting too much current through them. So this blue LED has a maximum current of about 30 milliamps. Now there's another type of common diode that we use in mechatronic circuits called a photodiode, and they're the opposite of LEDs. These types of diodes allow current to pass through when light shines on them rather than the other way around. The amount of current that's allowed to pass through this diode is proportional to the amount of light that's received by it, and these are commonly used as ambient light sensors to detect how much ambient light is available, for instance in a night light sensor, or in your car when activating automatic headlights, for instance. The bottom left of the slide shows a light measurement circuit where we can detect how much light is, how much ambient light is input to the sensor, and you can see it consists of a voltage source, a resistor, and a photodiode, and we measure the voltage drop across that resistor. Remember that the amount of current that can pass through this photodiode is determined by the amount of light it receives, and since V equals IR, then by measuring the voltage drop across the resistor, that gives us an indication of how much current is flowing through the diode and the resistor, and then we can determine how much light is shining on that photodiode. A common type of photodiode is shown here. A common model is made by Texas Instruments, and it costs in the $9 range or so. Now, one last circuit element that is really important for mechatronic systems is a flyback diode. Flyback diodes should always be used in concert with DC motors to make sure that you don't damage the switching elements in your circuitry. Let's look at why we need them. First, let's start off with this example circuit where we use a switch to turn a motor on or off, and that switch could be a mechanical switch or it could be a transistor, which is what it usually is for mechatronic devices. Now, in normal operation, if that switch was closed, current would flow from the plus V down to the ground, and it would flow through that DC motor. Even though there's a diode in a parallel path there, that diode is reverse biased, so there's a huge resistance there along that current path, so the current's not going to flow in the top path, it's going to flow down through the motor, and the motor's going to turn, and everything will be fine. Now that motor has a high inductance, L, so when that motor is switched from on to off, what happens is there's that constitutive relationship. Voltage is equal to the inductance times the derivative of the current. So as soon as we turn that motor off, the derivative of that current is very high, and it leads to a very large voltage across the motor terminals. So let's look at what happens in more depth. As soon as you open that switch, a high voltage is placed, then a high voltage occurs across those motor terminals because of that high inductance. Now, when that's the case, there's a corresponding high voltage then across our switch. And what can happen is if our switch, for instance a mechanical switch, just as it's open and that very large voltage develops, you might see some arcing or sparking, which can wear out our switch if that happens repeatedly, or that high voltage that's across our terminals there, our switch, if it's a transistor, can actually blow out our transistor. So we need a way to kind of dissipate that voltage or that current, and what happens is by placing a diode in a parallel path here, it provides an alternative path for the current that develops because of that very large voltage. So as soon as that large voltage is developed, we get a lot of current as a result, and that current is then going to flow around that circular path through that diode and then back through the motor and then back through the diode around in that path counterclockwise in this diagram, and it gets dissipated into heat fairly quickly. Without that diode, the only path that current would have to take is through that transistor or through that switch to ground, and that's what causes to blow out a transistor or cause arcing at that switch. So we always want to include a flyback diode anytime we're switching a motor on and off, and all we have to do is place a diode across the motor terminals, and that's basically it. To summarize what we've learned in this lesson, diodes are semiconductor devices that are used to control the direction of current flow, and they're used often in mechatronic devices. Light-emitting diodes are a special kind of diode that emit light when current flows in the forward bias direction. Similarly, photodiodes allow a varying amount of current flow depending on the light level. Now, flyback diodes are necessary in switching circuits where we have motors to avoid damaging mechanical switches or transistors.